I guess we should kick it off, huh?
Yeah, let's do it.
All right. Welcome to the High Performance HVAC podcast. I am your host, Adam Mufich with National Comfort Institute, tongue twister. I'm here today with my cohort, Casey.
Casey Contreras.
Yep. And then the man, the myth, the legend. He was doing VRV before VRV was cool.
We're introducing Chris there for a second.
Chris Hughes. Now with the Energy Conservatory.
Right.
And then the one and only Roman. How do you say your last name? I feel like I always screw it up.
Baugh.
I do definitely have always screwed it up.
It's okay. It's German-Irish, so I think it is actually Baugh, yeah. I don't care. Roman Baugh.
You can call me whatever you'd like. My wife does.
That's the joke.
Yeah. So what are we chatting about today, fellers?
Cold climate heat pumps.
Cold climate heat pumps. Hopefully some inverters sprinkled in there.
Yeah. So it's funny. I saw a post that you made. I don't know if it was today or yesterday, but you forgot to turn your sprinkler off in Florida.
It's Florida. Like we don't expect Florida weather to get down to like 20 degrees with like an 8-degree wind chill. And so, yes, I forgot to turn my sprinklers off, and it soaked my entire house. It soaked my tree. It soaked my heat pump, my AC unit, to the point where it actually blocked the lower housing airflow grill on the outdoor unit. And so it like derated my capacity by a lot. Something you don't expect to have happen.
Yeah.
And, because I'm in Florida, right, you're like, well, it'll just melt. It did not melt. So I had to go out there with a water hose and hit it with like 70-degree water from my well for like an hour to get it off. But it's just one of those things where like you don't think about those things, especially not in a Florida climate, of how cold it actually gets, or what ice does when it melts off of a heat pump, and where does it go, and when it refreezes, and what do those defrost cycles look like. Those are things like we take for granted here in Florida. Like people see frost on their coils and they start to panic. Like they literally call us and they say it's not supposed to do this, right? It gets ice, it gets frost, and then it goes and then there's steam, and like there's something clearly wrong with the system, and it's like, no, that's just a heat pump. You don't see it in Florida, and so it naturally people freak out. But yes, I did make that mistake.
And that's interesting. You have a cold climate heat pump. Am I wrong?
No, you're right.
In Florida. That's
we
that's
have the same
weird.
unit.
Is that like a weird thing?
No, it's funny, too, because the unit I have is actually compatible also with a gas furnace to do dual fuel if I wanted to. So I have 4 indoor units connected to 1 outdoor unit. And it's the same series of equipment you have in your house that you got because I told you should do it. And it's 100% heating capacity down to -4 outside. Not that I will ever need that in Florida, but I don't have any electric heat. I don't have any resistive heat. I don't have any backup heat. It's just, that's it. It's the heat pump heat, and that's it only. And I mean, last night I was clocking, even with 8-degree wind chills, and you can hear it whipping, you can hear it hitting the coils. It makes that like whistling noise where it's hitting the fan motor, stuff like that. I was still delivering 168-degree hot gas to my indoor coils, and I had leaving temps of 100 to 105 liquid temp off my coils. And so, for a heat pump, that's kind of unheard of.
Yeah.
I've got discharge temps of like 130 to 145 degrees off my coil, which again is unheard of for a heat pump. When you think natural gas or a gas furnace, people love that hot heat. There's that, you think heat is hot, but whatever. But with a heat pump, in cold climates, especially low ambient heat pumps, they still have that ability to deliver some serious heating capacity when it's cold outside.
Right. That's like a funny thing because everyone's like, well, you're going to have really lukewarm or room temperature supply air.
Yeah.
But you actually start looking at cold climate heat pumps, and they have some power. They got some power behind them. So real quick, Roman, we're going to get to some other things and nuances on cold climate and that. But I want to ask you, what are certain things that are very specific about cold climate heat pumps that are different than maybe some traditional styles?
Yeah, so when you're talking cold climate heat pumps, it's not going to be your standard split system. You have to remember that a single solid-state compressor, right, that has one speed, it can only run at one speed. And so the way a cold climate heat pump works is you have to usually have either a rotary compressor or a smaller scroll compressor. Most everybody uses rotaries, whether it's a swing or just standard rotary. And then they have the ability to overclock it. And then there's 2 things every cold climate heat pump has, one or the other. And so it's either vapor injected compressor, right, where they can take vapor and they can inject it in the scroll set midway through the compression process and load it up to increase.
Why would you want to do that? What's the point?
Lower compression ratio, right? So when you think about cold climate heat pumps, if you've got a heat exchanger that's outside in 10-degree weather, well, your evaporation temp has to be below, right? Your saturation temp of your suction line has to be below 10 degrees to reject heat to the air. And so you're running suction pressures and suction saturation temperatures of somewhere close to 5 degrees, 0 degrees, maybe even in the negatives. And so that's what, like 30, 40, 50 PSI in R410A? It's really low. And so because of that, you have a lack of vapor, quality of vapor, right? You don't have that much. And so you have all this extra space in the scroll set when it goes to compress it, which results in high compression ratios, right? That's where we start to lose that heating capacity really quickly. And so what do? Well, you can do one of two things. You can either inject it into the compressor with vapor injection through midway of the compression process and increase that, right? Lower the compression ratio, increase the head pressure, increase the heat that you're delivering to the space. Or you can do hot gas bypass, which is where you inject hot gas back into the suction line at the suction inlet, or at least upstream of the suction accumulator, and boost that suction pressure up to then bring the saturation temperature up to then load the scroll plate up again naturally and then run it that way. And so those are the two methods for low ambient heat pumps. And then again, overclocking the compressor, being able to turn it up over 50% speed, right? 150% capacity gives you also that ability. When you couple those two things together, then you can deliver some serious heating capacity at really low ambience.
Okay, I have two questions.
That was a lot.
Yeah.
So,
All right.
so I'm stuck on something when you were talking about water spraying on your coil. Let's go back to that for a second.
Yeah.
So,
That was like
Stupid thing I did.
5 minutes ago.
so
He's
I
catching
know-
up.
I know commercially, like the VRV, VRF lines, they do independent defrosts, right?
Yeah.
They layer it. They
Yep.
go up, down, up, down. I'm not sure if the residential lines have it to where the condenser coil or the outdoor coil is split, where they defrost top and bottom, or is they only doing one layer defrost?
No, so you're thinking of like simultaneous defrost, where you can defrost the unit to the left and then
Yeah.
defrost the unit to the right, and that is like nonstop heating capacity.
Is residential doing that yet? Okay.
No, it's because it's one heat exchanger, right? So
Yeah, okay.
they don't have the ability. And remember, when we talk residential markets, we're talking about making units smaller, lighter. When we go to R32, we gave a 40% reduction in charge. So, these units are getting smaller, so they're not going to add more coils and then a second expansion valve and then split them. And there's just no need unless you're going to do heat recovery, which some manufacturers have single-phase heat recovery. But I don't know if they have split coils. It's a good question, though. But it's cool, though, because you can defrost without ever turning off.
Yeah, that's what I didn't know if that was in the residential game yet. But
Only commercial, from what I understand.
My second part of that was with I've never experienced this, but the idea of water being at the bottom of the condenser coil and then freezing and then busting the refrigerant line on the bottom of that coil.
Yeah, crushing
right?
it.
So I have some package units at TEC that I've installed, and we have ran them real low, like to the point where I went on the roof and we were starting to get to like 0 degrees. Now, these are basic heat pumps. They're not cold climate heat pumps, but we're pushing them.
Yep.
And I noticed that, and these are, I'm not going to name names.
Sure.
But there's
Insert brand name
there's-
here.
yeah, insert brand name here. There's weep holes that are part of the bottom of the outdoor section of the unit. So the defrost water is not running out and down. It's literally running down in. So your curb adapter is 4 inches shorter, and the water just falls straight down to the slant side of the curb adapter.
Yeah,
so it's doing a good job of mitigating the defrost water down and out. But on the outdoor unit with water hitting it, were you watching for like freeze patterns and making sure you didn't bust?
Oh, yeah. So when I went over there, first of all, you could hear the fan motor clunking against the ice that was in there, which is a dead giveaway. And then the second one was just that when I, melted it, that was my biggest concern, was that the water that had, accumulated inside the unit was thick enough to impact the coil at the bottom. Because what it'll do is actually it'll grow bigger and bigger and bigger. And as the ice freezes, that water, it's going to expand. And that expansion will actually crush the copper tubing at the bottom. We see it a lot in commercial applications, but and it'll completely crush it completely to where either there's no flow or it creates a leak in the coil itself, which is why every VRF manufacturer, for the most part, has the bottom row of the coil is always getting hot gas. It never goes into an evaporative state, and it's for that reason there. Because when they defrost the coil, they want to leave a good 6-inch gap at the bottom so that it never freezes and it always drains out.
Even residentially?
No, so residential, you have to either get a resistive base pan heater, which is an accessory for every mini split. Every manufacturer makes one. Or you can get some of the newer mini splits that are coming out that actually have a hot gas loop that's on a solenoid that they will defrost the pan when they're going into defrost. So they'll go into defrost, and they'll also energize hot gas loop at the base pan. So it's not resistive heat anymore at the base pan. It's hot gas.
Hot gas heat for the base pan. Interesting.
It's like an intelligent defrost pan heater.
So how is that? How is the base pan heater controlled?
So usually, if it's resistive, it's going to be just a 120 volt relay on the board that says, "Hey, I'm energizing defrost cycle. Also energize the base pan heater," so that when the water falls off, it continues to fall out of the unit from gravity and not pool up in the base of the unit.
I think what you're asking though is it driven by outdoor ambient temperature on a sensor on the outdoor of the coil, or are they actually doing something different to make sure that they're not running defrost when they don't need to?
Yeah, so
not defrost, pan heater.
It's not all the time, right? If it was all the time, it'd be a waste. If there's no water coming off the coil actively, then you don't need to heat the base pan. It's probably, and I don't know the exact numbers from each manufacturer, but it's probably either 30 seconds before and then probably a minute after or something like that. Just enough to, again, we want to get back into that cycle of freezing water and running an evaporator on the outdoor unit, but also enough to get the water clear of the base. That's the biggest thing.
So it's timed more than it is demand for the base pan heater.
And every manufacturer is different, because we talked to Hitachi today at their VRF booth, and they were talking about how they have an intelligent defrost now in their VRF product line, both single-phase and three-phase, where they look at outdoor fan motor amp draw, and they know that when the coil is below freezing and it's like at 0 degrees, and they know they've run this many minutes in a heating state for the outdoor unit being an evaporator, and they see the amp draw climb on the fan motor because the coil gets impacted with frost because of restriction, then now we defrost. If there's no elevation, it is really slick, right?
Really slick, yeah.
So even if it is below freezing, but the humidity is low in the area, then there's no frost. And so if they don't see a fan motor amp climb, then they won't defrost. It's crazy, right?
That's pretty smart.
That's one of the things I've noticed, and I wish they did a better job at my heat pump in my house, is that I see it going into defrost when there's no frost on the coil.
Yes, and you're like, why? Why are you doing that? That makes no sense.
Yeah.
Again, you're losing heating capacity. And there are settings in a lot of units to where you can go back and you can say, hey, don't defrost, defrost longer, right? Or defrost shorter, or defrost more aggressively.
The problem is, though, when I'm in Chicago, so the problem is in, outdoor temperatures that are a little bit more mild, it needs the defrost.
Yeah.
We need that more frequent defrost cycle. But when it's really super cold outside, you don't need it.
So dry, right? There's no humidity. And so I'd love to see either, again, math equation go into that, which again, Hitachi's doing that now with the fan motor amps, and I think it's genius. But then, or just, I don't know, humidity, right? Figure out what the dew point is and see what your coil looks like. I mean, and not that anybody wants to have a humidity sensor outside. That's kind of
also a twofold game. I mean, if it's going into defrost all the time, it could just be dirty, and so that's like an indicator that your system needs to be clean.
Well, I don't know. I have my house before I came to AHR. It wasn't heating correctly, and I looked at it over Cool Automation to find out that it was actually undercharged. I had trouble maintaining my house last night and heating for some of my zones. And I noticed that when everything was on, my compressor discharge temps went up to like 230, and then it went into low pressure step down, and I was like, well, that's not normal. And come to find out, my unit wasn't defrosting at all, and the reason it wasn't defrosting at all because it wasn't charged correctly.
Let's pump the brakes real quick. All right, so you're undercharged. So let's look at let's talk about what was the RPS. First off, what is RPS?
RPS is revolutions per second. Most manufacturers publish their data with hertz, right? HTZ, I believe it is for most manuals. But RPS, right? Revolutions per second is what we usually clock it on service programs. And again, you can convert that to RPM because remember we're talking revolutions per second as opposed to revolutions per minute. So
what were you seeing as far as RPS?
So RPS
on undercharge situation in heating.
Undercharge situation in heating, because I have 4 zones. I had 2 small zones calling. There were 9,000 BTU units. 18,000 BTUs calling for heat. RPS was like 45. Max speed is 105. So it's like middle of the road, 50%. And then when my large zone for the main house turned on, which is a 3.5 ton ducted unit, FXTQ, then you saw a compressor ramp up, right? So more flow, more hot gas to more units, right? Compressor needs to ramp up to increase head pressure, to increase discharge temps. And so it would ramp up, and it would get to 90 RPS, and it got to 105 RPS. And even at max compressor speed, it still couldn't hit the saturation target for discharge. Right, the saturation target for discharge temperature was 115, and it barely got to 101, 102 at full speed. And so, it's sitting there chugging away as fast as it can go, and it still can't create high enough head pressure, right? Because remember, head pressure converted to saturation temperature can't create high condensing saturation temperature to meet target, and so wasn't hitting targets, and then suction pressure dropped.
So let's talk about EEV steps. What were you seeing indoor and outdoor EEVs?
Yes, outdoor EEV wide open. So my outdoor unit, which is an evaporator at the time, was starved. It wasn't getting enough gas. Yeah, it was trying to get more gas. It was wide open, and it wasn't getting enough gas. And then you saw the suction superheat climb. It was like 5 degrees, and then it was 8 degrees, and then it was 10 degrees, and then it was 13 degrees, and it jumped to 25 degrees, and it hit 38 degrees.
Well, can I ask a question clarifying that? When the 2 stages were open only, what was your
suction superheat
with the 2 zones versus?
It was like 8. Yeah.
So it was maintaining kind of.
Yeah, no.
And then when you open up that main zone, that's when you started to see boom.
Because it was like, let's
EVs
go.
Trying to flood. Superheat's drifting far apart. And it's like, we don't have the capacity.
Well, so when so the unit, again, it's a 5-ton outdoor unit, and it has a 5-ton rotary compressor, but it was only running 18,000 BTUs, and so it was running at a speed that is conducive with 18,000 BTUs. And guess what? My unit has enough charge for 18,000 BTUs. It looked perfect, but as soon as the demand got higher, and I increased the flow and the capacity because I got a 3.5-ton coil that's now calling for all the hot gas, along with the other 2 units. It was too much. And so it ramped all the way up to meet the demand, and it found that when it ramped all the way up to meet the demand, suction superheat climbed through the roof, then discharge superheat followed right behind it in the same pattern, right? Because we weren't getting enough vapor back, and then it just...
So I have a question for you, Roman.
Yes.
You're going to go home, and you're going to fix the leak on the system and repair it, right?
Actually, I think I messed the charge up myself. Adam could feel the pain on that one.
Gas and go. Gas and go.
So
I already know how low it is because I had a guy come to my house.
Did you really?
I did, yeah. I was looking at the data at 1 a.m. last night. I got is this an EEV problem or is this a charge problem? And I forgot that when we installed the whole house generator on my house, finally, Kalos did it, and I moved my outdoor unit because it was in the way. And in moving the outdoor unit, I pumped it down into the outdoor unit and then recovered the charge. But I didn't add the charge back that I recovered from the line set. And so here we are. And it was great. Again, we've had it for probably 8 months now. It was good for summer.
Yeah.
And then, you hit winter. And
yeah, I think there's a lot of confusion in the question I'm going to ask in the marketplace. And
sure.
I look at you as the super pro of this world, okay?
Well, I don't know about that.
And so how does Roman charge that system?
So 100% capacity, right? So when we talk about systems, whether it's a mini split, whether it's VRF, it's running it at the rated capacity. So if it's a 2-ton outdoor unit, then I need to run exactly 2 tons indoor for heating capacity. And
what does that mean?
What?
What does that mean? You're running exactly at 2 tons. Like, how do you confirm that?
Well, so that's the thing. So if I've got a 2-ton outdoor unit and a 2-ton indoor unit, it's just 1-to-1. Then I'm going to turn the heat on and I'm going to turn the temperature way up, so it doesn't satisfy.
But okay. Let me add a layer of complexity.
Sure.
It's not warm outside.
It's not warm. It's cold outside.
Let's just say it. Let's say it's 40 degrees.
Okay.
What am I doing now? Because there's some holdbacks in this equipment when
this just happened with me. I called him on the phone. I'm like, dude, you gotta help me. You gotta help me.
I think everybody needs to hear this.
Yeah, so it does change. Like, so you're asking, what do I do if the ambient temperatures outside are
yeah? Are you weighing it in and coming back in dead of summer to check charge?
I have done both. So I'm very comfortable with just shooting from the hip and just doing exactly what I know it's supposed to do, and then looking for the things that I know make sense, and that is suction superheat, discharge superheat, and system subcooling. Again, a system is going to balance at some point on all the sides, right? The outdoor expansion valve is going to stop going up and down. It's going to stop in a sweet spot.
So would you be running it in heat mode while you're doing this and trying to set this initial charge? So,
yep.
So
I can charge it in heat.
So I'm getting really granular here, but I think this is good content, right?
Yeah.
Like let's just say the system went flat. You don't know the system. You show up to a house. It's got
in the walls, lines are everywhere.
Yeah, you're like,
can't measure
man,
it.
what do I do? Like, do I pluck an initial charge that I think should go in?
I do.
Set an additional charge, get it running, and then start evaluating the data and beef it up as we go.
Well, that's it. Yeah. So I'm going to look to make sure none of the sensors are bad first, because that's going to throw you off right out the gate.
And you're doing that from
my phone, my Bluetooth adapter, a service device, from
Okay.
the thermostat. I mean, it's really depends upon the brand.
Okay.
Wherever I can access it, that information. Going to make sure that everything's copacetic, especially if it's 10 years old or it's 10 years or older. I got to check that base first, because if you jump straight into charging a system and the sensors are off by 10 degrees, it is going to screw you up so bad, because the science won't make any sense, and then you'll be like, well, this doesn't make any sense even more than it did the first time. And so it adds to the problem, and you won't know it until you finally give up and turn the dang thing off and let it equalize to find, well, the sensors are freaking bad. I had a company that did that in Michigan the other day. They were like, oh man, I don't know where the hot gas is coming from. My suction temperature in both units, right? This is a 13-year-old system. Both outdoor units, suction temps are at 135 degrees. And he's like, I don't know where the hot gas is coming from. I checked everything. I checked this pipe. I checked this pipe. I checked everywhere. And I'm like, whoa. Look at the system. And he's like, what? And I'm like, look at your discharge temperatures. Your discharge temperatures out of your compressor, the hottest part of the system is 109 degrees. You can't have a suction line that's hotter than the hottest part of the system. It's physically impossible. So the 135 is bad thermistors. And you go and you look at it, and the temperatures on those thermistors never change the entire operation.
So slow down. Back up a second. All right,
It's gonna
you're
be one of
talking
those
way
podcasts
too fast.
This is one of those podcasts you're going to play it in like 2x slow, not 2x fast.
Yes, go ahead.
All right, so just repeat what you said and talk to me like I'm 5.
Sure. Okay. I've got a 5-year-old. I can do that. So when we talk about refrigeration systems, there's a spot in the system where you expect it to be, one, the coldest, right? And that's going to be after the expansion valve, right? In a low pressure saturated vapor where it hasn't changed from a liquid to a vapor, but it is in low pressure state, right? It's a slurry. That's the coldest part of the system. The hottest part of the system is directly discharged from the compressor. Those are two things that we know to hold true in all refrigeration systems, right? Unless we're injecting hot gas from a cascade system, or we have some kind of, inline heater that I've never heard of, that's adding heat to the line, which, base pan heaters laying on the refrigerant line, sure. But when we're talking about refrigeration, just at a basic core, there are two spots, the coldest and the hottest. If those are my reference points, right, it's going to be those spots in the system, but also the saturation temperature in those spots, because they're going to match, right? Leaving my expansion valve, maybe it flashed a little bit of gas, sure, but it's going to be within 2 degrees of my suction saturation temperature. It's at saturation. We know that to hold to be true. Discharge line, right? We know what my saturation temperature is there because of my pressure, right? We convert our discharge pressure to saturation temperature. That's going to be the hottest part. That's where we get discharge superheat from. If my suction line is 135, but my discharge line is 109, I physically can't have a 135 suction line. I physically can't have 135 anywhere in the system.
Right. Impossible.
It's impossible.
So when you're doing a thermistor check as your first initial thing, in my mind, I would have this, how I think about this, I'd have the system off. It's flat. I show up. Everything's not running. I could kind of use ambient air as a way to say, boom, let's see if it matches ambient air. Is that a good check?
Yes.
Or would you want to run it and check it to make sure that sensors don't change as they change temp?
You think about the one sensor in any refrigeration system that sees the least amount of stress, and that's the ambient air temperature thermistor. It's never above 90, and it's never typically below 60. And it's always sure, in Florida. But to that point, and even the outdoor sensor, right? It's going to be it doesn't live in the inhospitable environments like a suction thermistor does in a heat pump, where that line is really freaking hot, and then it's really cold, then it's really hot, then it's really cold, especially in the shoulder season, or in the summer where it's always cold. And so, your ambient temperature thermistor is always your baseline for a system. And if you want to speed that up, you can run the indoor fan so it equalizes the sensors faster. Can't really run the outdoor fan. But.
So thermistor check, then initial charge?
No, then I'm putting in the exact weight that the outdoor unit comes from the factory with.
That's if the system was dead flat when you walked up to it.
Dead flat. Or I recovered it.
You recover it and then put in the condenser
Sure,
charge
maybe
just to get some level of knowledge about what the system holds.
Sure. I'm going to start at bare minimum as if I don't have a line set. Then I'm going to build from there. And if that's
Meaning
a pound,
you run it and then start building up.
Yep.
Okay.
I run it, and then I'm going to add. So let me look at the system. If it's a 5-ton, I know that my charge on the outdoor unit is probably going to be close to 8 pounds. And then how many indoor units do I have? Am I over-connected? Am I at the connection? Is it 1-to-1? If it's 1-to-1, then I can maybe think that I'm going to be another 2 to 3 pounds. And so maybe I start with the base charge, turn it on, add a pound, wait 15 minutes, see it equalize. What does it look like now? Okay, add another pound. I'm at 2 pounds. I know that when I get to the 3-pound mark, I probably am not going to want to go over that without looking at everything to see if there's a problem.
And you look at, like you said, there's 3 different metrics you're looking at the entire time. So it's not like a regular, straight cool system where we're at TXV. Obviously, it's in heating, but straight cool AC, TXV, you're looking at subcooling, right?
Sure, yeah.
You're paying attention to superheat to make sure you have a TXV functioning properly.
Correct, yeah.
If it's a fixed orifice, you're looking at superheat and cooling.
Airflow's a big one,
right?
too.
But you're looking at system superheat.
So I'm looking
Suction
at suction
superheat. System subcooling.
We're running in cool mode.
No, heating mode. Heating mode.
Heating mode. Okay.
I'll do both.
Okay.
Yeah, but you're also paying attention to something in residential we don't look at.
Yeah, discharge superheat. So suction superheat, discharge superheat, system subcooling.
And you kind of like triangulate, which is super cool. What do you call it?
The troubleshooting triangle.
Troubleshooting. That's if I had a bell, I'd ring it. That's a trademark, right?
Not yet.
So could we get? Can we hit that second one? I don't know if I'm super familiar with that.
Discharge superheat?
Discharge superheat.
So discharge superheat is the quality of compression leaving the compressor. So in suction superheat, I want to make sure that we're measuring, the superheat on the suction line, so there's no liquid coming back, right? If the purpose is, am I getting good heat exchange, or am I picking up way too much heat? Am I not doing enough vapor? That's suction superheat.
Yep.
We measure the same exact thing on the leaving side of the compressor to measure the quality of compression, discharge superheat. And they usually go hand in hand. So if my suction superheat is high, right, and my discharge superheat is high, it's because I don't have enough vapor coming into the compressor.
I hate to do this to you guys, but I got to ask, when you say discharge superheat, where's my reading at?
6 inches upstream of the compressor on the discharge line.
On the discharge. So I'm reading discharge line
temperature
and
subtracting it from condensing saturation temperature, which is your head pressure at saturation.
Yeah, I just never use that metric.
Well, so if you look at the actual, pressure enthalpy chart, right? The PT chart, the rhombus I think it's a rhombus. Probably not the right geometric shape, but it's close enough. But in the top right-hand side, that triangle that it goes past the line is discharge superheat.
But let me. You just said the condensing.
Lines,
yeah, that's
right?
it. Yeah. That is discharge superheat.
Okay. You're connecting dots for me that.
If you connect those 3 corners, that's the triangle.
But so you said the saturation temperature
at that pressure.
Yeah, but it's not really saturated at the discharge, right?
No, it's not saturated. The saturation temperature of that pressure is your baseline measurement. How much over saturation temperature am I? Am I 80? Am I 30? Am I 2? Right? Those are going to tell me.
What is a normal range for that?
It's usually between 32 and 70 or 72, around there.
Oh,
I like to see 54. Well, inverter compressors have a wide range of speeds.
Oh yeah.
Now Copeland has discharge superheat.
Max speed. At max speed, what does that kind of normally look like?
Again, it depends on load. I like to see 54. Like 54, 40, 58, somewhere around there. Like, again, there is no right number. Every system is installed differently. Airflow's different. I mean, all these things add up, right? So you can't just say it's always got to be 68. And it's like, no, the real world isn't like that. We have to have a buffer zone because everybody's piece of equipment is different. But I like to see around there, right? We never want to see it on the high end. We never want to see it on the low end. Around the middle.
Do you have to go to equipment specific training to learn what they set for ranges for that?
No, I did an interview today. The Copeland app, yes. Copeland app has got so much cool things that they added to it here that they unveiled at AHR. And so, on their new app, right? What's old app, but new features, they have all that stuff. Where they're actually going to show you where in the compression envelope your system actually is. Are you outside of that compression range? Because if you are, the compressor's not designed to run in that range. Find the problem.
That's pretty cool.
Yeah, it's a really cool app. You don't have to be an engineer to do that anymore.
So there's a lot. You're looking at all kinds of different things, right? We have 3 different metrics for charging, but you're also looking at like EEV steps, indoor and outdoor. You're looking at compressor RPS. So all these different aspects, you're kind of putting the pieces together to try to tell you
where they fit. Yes, into the puzzle, right? So I'm teaching a class tomorrow at 10 a.m. In room, I think it's S219. About how to use that triangle to find problems. And on that triangle, you put the compressor, you put the outdoor expansion valve, you put the indoor expansion valve, and all those things are going to tell you what's going on with the system. Again, remember, an electronic expansion valve is designed to meter refrigerant. And so either if it's wide open, it's not metering refrigerant anymore. And so, it's just one of those things where if it's wide open, it's not metering refrigerant. If it's all the way closed, 20 pulses at a 2,000, then it's getting too much refrigerant, right? And so what does that subcooling look like?
So all those things add up when you're trying to troubleshoot a system.
So let's shift gears, if you guys don't mind, for a second.
Let's do it.
I want to talk about, Chris and I had a conversation a couple weeks ago because you were replacing those package units, right? And you were trying to recover the refrigerant in order to recycle the units.
It sounds like a good story.
So-
it was an interesting thing I've never dealt with.
Oh, nice.
Because I moved to.
Oh, that's
cold
right. You were
weather.
telling me. Yeah, no,
And
I
so-
remember this. Yeah.
So we're heat pumps, right? That is huge super push right now. And so the 2 package units I took off the roof, I set them in the parking lot, and I was like, I'll get to the refrigerant recovery later, and then I'll have a scrap man come, haul these things off. Well, we really wanted them gone. The weather wasn't working with us. So I was like, well, I'll just go recover them. And the day I chose to do it, it was 8 degrees outside.
Gosh.
So I went down to the local supply house and bought a brand new A2L recovery machine.
Nice.
And
Don't
it's
name the
warm, right?
brand.
It's not. It hasn't been.
Insert brand name here.
Yeah. And so I'm like, okay, well, I had some recovery tanks. Long story short, that I kept to myself, and I hauled them up north with me.
Sure,
Everybody's
yeah.
got their secret stash of stuff.
Sure.
And so I'm like, they're R22 package units. I was like, well, I'm gonna go suck the refrigerant out.
Yep. Easy peasy.
I go run a cord. I do everything. I even pack the refrigerant tank down with some snow to cool it down.
Nice.
These package units don't quite have any snow on them, but they're out in cold weather.
Sure.
I pull the recovery machine out there, which is from a warm environment. I set it in there and I try to recover the refrigerant, and it doesn't work.
No.
The recovery machine just trips, and it trips, and it trips. But I'm looking at the pressure gauge on my recovery machine, and I have pressure. It's not running in a vacuum. Okay, so I'm like, well, why is it tripping? So then I go to the literature of the pump, and it says, oh, it does not work below 32 degrees. Fast forward a couple weeks, and it's 36 degrees outside. And I'm like, well, I'm going to go finish that job now.
Doesn't
I
work.
go put it all out there. It still doesn't work. Same problem. And I've got pressure. And I'm thinking, okay, I don't understand why.
You got a lemon.
Well,
obviously.
maybe. That's a conversation maybe I'll have at this show at a different
Tomorrow morning.
Right. I was talking to Ty about it, and it seemed like every pump, I don't want to generalize, but every one we were looking at all had the same 32-degree threshold.
You gotta
And it was
you gotta crank it up inside and then bring it out.
Well, it's something I think that should be discussed, and what I'm generalizing is saying maintenance about heat pumps in cold climate while it's cold outside should be a discussion. Jim Bergman made a video about, pulling a vacuum when it's freezing outside and the difficulties of that. And I'm experiencing this refrigerant recovery in cold climate, and I've got complaints.
Yeah.
And there's workarounds. We could tent over the unit, put a heater in there, and heat it up.
Yeah.
But that is adding some major complexity to the repair.
It's not easy. So you'll see a lot of these commercial VRF guys that do a lot of this stuff in Canada, where that's just every day. And they got the whole setup as gas heaters, gas-fired heaters. They've got their gas tanks. They've got to get everything fired up. They tarp it. They tent it. They put up fake structures. They do all this just to pull gas to change a compressor out in the middle of a snowstorm, or even when it's 8 degrees outside. This is all these things they have to think of that.
And you've probably seen that in your world some. For me, I've never seen anybody do that.
Gotcha.
I was insulated to it, I guess.
Yeah,
so
yeah.
I've never seen any images or anything.
You got to remember, he's from Florida. I don't know what he's going to see in his world.
Well,
And I still have ice in my yard, okay?
Yeah. And I was in
Once.
Louisiana, so I never dealt with any cold climate problems. But so I reached out to some local guys. I'm like, what do y'all do? And surprisingly, a lot of them are like, well, we don't really deal with that much.
Yeah.
We don't push and pull refrigerant that much in the winter.
Yeah.
Because heat pumps really aren't big up there yet.
Yeah,
in my
yeah.
opinion.
It's just gas furnace problems that they're dealing with, and there's
And
not
so
a
they're
lot of
go-
heat pumps. But
And then one guy told me, he's like, he goes, honestly, we'll just postpone that part of the job till it gets warm. He goes, because a lot of times we can't even get the outdoor unit off the ground because it's frozen to the ground.
yeah, no, that's a big one too, right? We need to go out there with a heat gun and just heat it up.
Yeah.
But I have seen people do that though before too. We've had problems where, up north, even in the wintertime when we go to turn on systems and we'll go out to do factory startups on new equipment, and you'll find that they didn't turn the power on until you rolled the truck up. And when you do that, and it's again, it's 25 degrees outside or 32 degrees outside, and those compressors are ice cold, you'll get ground faults on the unit just because of all the liquid refrigerant that migrated to the compressor.
Well, the oil's got to also be tacky at that point.
So we'll break out the heat guns and we'll just lay them on the compressor on both sides, and you'll have to leave it for like an hour for it to actually warm up, and before you can even clear the ground fault on the VFD drive for the compressor to get the unit started. Because we drove 3 hours up there, man. It's a lot of stuff that you got to think of when it comes to cold climates.
Yeah.
So, how do people learn this stuff? Is it just trial and error, or what?
I mean, it's refrigeration, right? It's understanding that we know that refrigerant migrates to the coldest spot in a system, and understanding that if that's outside, it's outside. What's all outside? What's my problem? What's the fault? If it's a grounded compressor, is there liquid refrigerant in the windings? Right? Does a crankcase heater work? And usually, most systems you're going to see that are heat pumps are going to have crankcase heaters, or they're going to energize the winding on the compressor to warm the compressor up before it tries to turn on. And so, you'll find guys up in Canada, well, they'll take their gloves off and they'll stick their hands in the blanket on the compressor to see if it's hot enough to stick their hand in there. And if it's not, then the crankcase heater's probably bad. I can't tell you how many compressors actually die in commercial VRF systems or commercial package units, stuff like that, because the crankcase heaters wear out over time because of how cold it is up there.
Wow.
Or if someone takes the blanket off the compressor with a crankcase heater. Like, again, it's those things that we don't think about where, like, when the system turns off, the crankcase heater isn't strong enough to overpower the outdoor conditions, and then the compressor grounds when it goes to turn back on again. And that's just because that resistive band heater wore out over time. And so you'll see these commercial compressors now where they've got 3 of them, where they've got 2, and it's that redundancy factor for where they install it. And so you're going to see more and more of that too. Stuff you don't think of.
I would think, and do they monitor, Daikin, you're a Daikin guy, but they're all the same, right? There's sensors all over the place. So
they don't want
as far as all the different...
they're exactly the same.
do they have sensors monitoring, the
compressor temperature?
Yeah.
So yes.
Can you tell if the heater is bad, just by looking at the D checker?
The further down the road we go with these systems and these compressors and these compressor manufacturers and mini splits, VRF, whatever it may be, they're putting now thermistors on the compressor body, whether it's at the top, whether it's on the side, whether it's a little bit away from the crankcase heater, and you'll be able to see what is my compressor body temperature. I was looking at Mitsubishi data on the flight in today. For a system in Boston that's having problems heating right now. It's 2-pipe heat recovery. And you look at the compressor body temperature, and it's like 50 degrees. But the discharge temp's like 180. And it's like, well, it was getting liquid back to it, but also I'm sure they pulled the blanket off, and the crankcase heater probably doesn't work very well. And so, having that data is important because now I can see 2 parts of the problem. I can see the discharge superheat, but I can also see the compressor housing shell and its temperature. So.
I have such a more deep appreciation for, back in the day, you'd have those big blankets over compressors, and I always thought it was for
the
sound.
Big train blankets, right? Yeah, the big
now
orange.
I'm like, they're
orange
probably
pumpkin.
for up north.
And then the mice get to it, right? And they start chewing it up, and you're like, you don't need this anymore. Just toss it off.
That's just hold moisture. Get that.
Same with the crankcase heater, right? It's like it grounded out. And we don't really need this. In Florida we could probably get away with it, but not up north. That stuff is a compressor killer.
Wow.
Small things you don't think about, man.
That's interesting.
There's also big things I don't think about.
Medium size too. You hanging out with Ty before you came on this panel? That's a classic Ty one.
Yeah. So no, there's so much. He blows my mind every time I talk to him. You're like the inverter wizard.
I've had my butt kicked by enough of them. And I've seen enough problems, and people have asked me enough questions to see their problems that I've been really blessed and fortunate to help people through their own issues. It's one of those things where you go and you do something, and it just chews you up and spits you out. Either you're going to quit and never do it again, or you've got to learn everything about it. And I was the opposite. I had to learn everything about it. And so it's just that on rinse and repeat. And then when people saw that I was doing it, they had questions for me. And then I got pulled into their problems. And then I learned from that problem. And so there was just never-ending problems throughout my career that huge exposure that led to where I'm at now, where it just, for me, it's second nature. But a lot of people, it's still confusing. And I get it. It is confusing stuff. It's not an easy topic.
I think you brought up a good question that I don't know if we gave the perfect answer to. If I'm a technician, and let's just say I've been in the 14 SEER single stage, 16 SEER 2-stage world, and I want to get into inverters, and I'm nervous because it's like I'm going to have to repair these things that I put in. What is the roadmap to become someone who does the installs of the high-end equipment?
You just jump in and do it. I mean, there's no like science, there's no method behind it. Like there isn't like a 20-step process to help you install inverters better, right? Follow the installation manual, take the classes, understand basic refrigeration principles and where they apply, superheat, subcooling, stuff like that. But
It is super important to follow the manual.
it is very,
It's very like, and that's one thing that that you look in some of these where it's like you should energize the outdoor unit should be powered up for sometimes they'll say 24 hours before you could start up the system.
yeah, because you got to warm up.
Right.
Because it doesn't have a crankcase heater; it's energizing the winding.
That's
which
like
takes time.
climate zone, 5 and above problems.
Well, there's other things too. There's different nuances. There's you're trying to evacuate the system. You're trying to pull a deep vacuum. Sometimes these EEVs come closed from the factory. You have to power it up and actually tell the control to open up the EEV so you could actually or flowing nitrogen, right?
And I'll tell you
when you're
about
brazing.
I'll tell you about a fun one. A 3-phase commercial manufacturer for VRF has a 460-volt system that they energize one of the windings all the time when it has power. And so if you pull a deep vacuum on the compressor while the unit is energized, because it has to be energized to open the valves while you're pulling this vacuum so no one can turn it on and you can get all the refrigerant out and evacuate it, you will ground the compressor out about 90% of the time. And so you'll go and you'll put a brand new compressor in, you'll pull a vacuum, come back the next day or in the morning, and then you'll find that your compressor is grounded. When you turn on the unit, the board blows up or it shows as grounded, and you're like, that compressor was good when I left yesterday. And it's like, well, because, again, it's one of those windings is energized, and you're pulling a vacuum, right? Less molecules in the vacuum, so the gap between the wire and the wall, it bridges the gap, and it'll pop it every single time. And not every time. I've seen some they get away with it. Maybe they don't pull a deep vacuum.
What's the fix?
You pull the wires off the compressor and
So you have
isolate
to-
them,
Wow.
and then turn the unit on.
Is that an oversight?
Is that one of those don't ask you how you know type situations?
I've had 3 inverter boards blow up in front of me where the plugs blow off the board and hit me in the chest.
Is that in the manual?
No,
That
it's
you should unwire the compressor when you pull it back in?
wear the proper PPE because you don't know where the boards are going to. So when we throw 460-volt disconnects to turn VRF equipment on after we change compressors, my guys have been taught to stand away from it. Right, you stand back. You don't stand in front of it. You don't touch it. You don't stand near it. You say a prayer. You burn some incense and maybe some rosemary. Say a prayer and then throw the disconnect and hope for the best because sometimes that's all it is. But you got
Louisiana,
it all.
We had a voodoo lady.
Is that what it is? Pull out your VRF voodoo doll and
Yeah, that's right.
say a few chants,
Yeah.
right? But that was it. Like that was trial and error. That wasn't in the manual. The manufacturer would admit to it. They don't show that it's connected. But we found that if you put a meter on it, there's voltage. And it's one of those things where you wouldn't know unless you had it happen to you over and over again. And so you'll get guys out there be like, oh, that's what happened to my system. I had no idea. And it's like, yeah, not a lot of people know unless you've done it enough and had failures because of it or boards blow up on you.
So we only have a few minutes left, but I wanted to touch. You guys are both familiar with Jim Bergman talking about.
I've never heard that name in my life.
Jim who?
He's like a not so well known dude.
Is it like measure slow or something like that?
Yeah, super slow. Unless you're Stephen Reardon, right?
Yeah, that's it.
Hey, no, one of you guys brought up about pulling a vacuum in cold climates.
Yeah.
Jim touched on that. Do you want to like vibe on that for a minute?
I don't know. We don't pull a whole lot of vacuums in cold climates. I still need to go back and watch that video.
But let's talk about the science behind it, right? Like when you're pulling a vacuum, and it's like obviously we're trying to boil off moisture, right? We're trying to we're taking all the moisture out. We're pulling it down deep enough where we're at a new saturation point where we're boiling off that moisture in the system. We're evacuating all the moisture out, and when it is super cold outside, it is possible to freeze some of the moisture in the lines, right?
Well, so copper has a really high thermal conductivity, and so if you've got a bunch of copper lines that are outside in a cold environment, then the copper could be cold. But I mean, I don't know where.
Like a super cold. Like, well, let's talk about. All right, so
I feel like
week, like a week ago,
Yeah.
we were, or maybe it was 2 weeks ago. I was It was -10 in Chicago. -10. So let's say
Why do
you're.
you live there?
I don't know.
What is wrong with you?
I mean, but like I get what you're saying. Copper has a really good thermal conductivity, right? So there's heat transfer from inside of the house to outside of the house. But I can't imagine it would be that great when it's negative 10 degrees outside, that if there's moisture in the lines or whatnot outside. And let's say you're doing a repair for an outdoor unit. You have a leaky outdoor coil or something like that.
I feel like we should get Eric up here because he just did a vacuum talk about this like recently on True Tech Tools podcast or whatever the show is. It's a show. Yeah, it's a show.
I think the answer is if you're in cold climate and you're going to be doing like heat pump repairs in that weather, you're going to have to build a contraption over the unit and heat that space up, and then those problems go away because you've warmed the environment up, and that adds time and complexity. Eric's saying no.
That's not how you do it.
Well,
Get up here, Eric.
There's a
here,
microphone
Eric.
over there.
We're going to hear from a special guest speaker out on the stage.
True Tech Tools.
Is it on? Can you?
Now he says it's on. Okay. So the number one thing is you got to keep liquid water out of the system, because if you have no liquid water in the system, you can't freeze it to a solid.
So we should not pressure test with water, is what you're saying.
Exactly. Don't pressure test with
But
water.
but nitrogen is
Oh my
not
gosh.
dry, right?
Correct. But if you use nitrogen that's already a nitrogen tank that's already below freezing, if it had any liquid water in it,
would freeze that
that's
tank.
already going to be frozen in the tank and not come out into that system.
Interesting. But I would still say refrigerant recovery is a pain in the butt. And so if I'm going to do a full repair I got to add refrigerant recovery,
I'm going to
gonna
ask you this,
hotbox
Chris.
that unit.
How do you think all of us up in the north have worked on refrigeration systems all winter long for years? Because I've been out in negative weather working on blast freezers and sub-zero freezers and things like that, because we've got to get them back up and running.
Yeah. So the only thing, and as you know, I'm not from cold climate. I've just moved up there. So I was asking a commercial guy the other day what he did for that. He told me he would tarp it and he would just blast heat, and he would heat the system up. And they would just use strategies like that. They're like heating the equipment up in really unorthodox ways.
You can, but if you get a recovery machine that runs low temperatures, then it works.
We should have another discussion about that.
That sounds like a long podcast.
Yeah, we're going to have a part 2. Eric's going to be involved in that one.
Hey, all you got to do is call me. Y'all know where to get a hold of me.
Absolutely.
It's going to be turned into like an 8-mic podcast.
Yeah, I feel like this was a continuation of the one that we did a couple weeks ago in Florida.
Yeah, inverters suck. Yeah. They don't suck, no.
So, I don't know. Any final thoughts?
Yeah, I mean, so, don't make it so complicated. We talk about all these things and this new technology and what we're doing with it. It's still just refrigeration systems. It's superheat, it's subcooling. Learn what discharge superheat is and, how to use it. Well, no, we have tech talks about it. We have tech tips about it. It's something that I knew nothing about like 4 years ago. And then I learned how useful it was. And then I learned to use that as a tool to troubleshoot. And it helped me track down the problems even more so. Compressors that were low in oil or stuff like that. And so don't overcomplicate it and just focus on the basics is my thing. That's what I harp on all the time. Focus on the basics.
Awesome. What about you?
I'm going to argue the fact that if I was going to repair systems, residentially speaking, I would probably invest in me an ice fishing tent and a heating system for it.
Eric says it's a waste of money.
Well, it may be, but I see setup costing me some time. But once I hotbox the outdoor unit, and I'm trademarking that right now, I'm hotboxing the outdoor unit. Then I can just go in there and
I would be
work
really
on
interested
it,
what your service ticket item looks like. Hotbox unit.
$400
$400.
setup. There we go.
Why am I paying for
mean,
this?
if that's if that's the system they want,
What kind of service
that's the
company we
repair I'm
working
going to
for?
have to make. I'm going to have to do what I got to do.
No, so understanding the science behind it, and then again, staying true to what works in your market is a big thing too. Like, don't let someone talk you off of what you do because you don't do it. Like, I live in a Florida market where it's sunshines and rainbows for most of the year, and we don't have to worry about that stuff. And so, I don't know a whole lot about it because I don't have to worry about it. So it's sometimes that education piece, it's out of sight, out of mind. So
Keep learning.
that's it. Never stop learning. And we could say the HVAC school motto, right? It's not. even though it's not a podcast for HVAC School.
Vortex Bitex? What?
I'd say that I have Brian's whole spiel down, but I don't.
Yeah.
So.
All right. Thank you, guys. I appreciate it.
Appreciate you, man.